We're gonna talk about HTTP and CDNs today, just like the Hypertext Transfer Protocol, which is what the internet is built on, and CDNs, Content Delivery Networks, which are like magic sauce you can just apply to any of your problems to make it go away and your website be faster. So, hi, I'm Pranav. There's some stuff about me. This talk is divided into roughly four portions, which are mostly not related to each other, but it also follows a basic framework. First, we'll talk about the internet, which is built on the hypertext transfer protocol and the transmission control protocols. And then we're going to look at two central problems that clients face and would like to solve, which is bandwidth and latency. We'll then look at how CDNs will help us with these problems. And then finally, this is like not related to most of the things, but to look at how to debug network errors, because it's nice to know how to use. Anyways, so why are we interested in bandwidth, latency, and speed in general? Because websites are getting larger, and the average web page size among the top 1 million websites, something past the size of Boom. And this was back in 2016. So web pages are getting larger every day, and we just need to get it to the end user quicker. So we'd like to optimize this. And usually the backend is optimized fairly well, and the same for all clients. So we would like to look at the link between the backend and the front end and how to optimize that, because that's where a bunch of the bottlenecks lie. So part one, the internet. Unfortunately, in our universe, everything, including information, can only be transmitted at the speed of light. And light is pretty slow if you think about it. It takes a whopping 1 nanosecond to travel 11.8 inches, and that's like a lot of time. It translates to 15 milliseconds from San Francisco to New York and 45 milliseconds from SF to Mumbai, which is like approximately where I'm right now. If I had to react to a thing that I know, like maybe Nicole is doing, it would take at least 100 milliseconds plus my human reaction time. Even in a perfect world, you need to wait for one round trip time, which is like twice of these numbers to confirm that your message was sent. What do we mean by that? Well, networks aren't reliable. So if you know how the internet works, there's a bunch of undersea cables and there's satellites and there's all sorts of computers, and computers can fail and sharks can eat the undersea cables and so on. Networks aren't reliable. So your message may or may not reach the destination. And if you want to be really, really sure that your message is reaching the destination, then you need to get a reply back from the destination saying that, oh, yes, I have received this message. This brings us on to the two generals problem, where there's two generals on two hilltops, and they want to attack an enemy who's in the valley between the two hills. But they will only win if both of them attack at the same time. So the first general, General A, sends a message to General B and initiates the attack, but he has to make sure that General B has received the message before he will actually attack. Now, General B will respond to the message if they've received it, and then General A can know that yes, they have received the message. Now, the problem is the spies or the messengers can be intercepted in the valley. And you can see how this is a problem, because for General A to be sure that General B has received the message, General A needs a response. But then General B cannot know if General A has the confirmation unless General A sends a response to the confirmation. And now we are in an endless loop of responses to responses and response to response to response and so on. So this, combined with the fact that we don't have instantaneous communication, makes ensuring that your connection with whatever server you have is healthy. And right now, the best we can do seems to be having timeouts. If you do not receive a response for the timeout, then you assume that the message is lost and resend the message and so on. Now, the other problem we need to worry about is message ordering. Messages can take various paths to reach the destination, because messages can be chopped down in packets and they can take various network cables and routes and so on. And so they are sent independently. The way we have decided to solve this is the transmission control protocol, which tries to solve the two issues we saw and forms the basis for most modern internet communications. So knowing how TCP works is crucial in understanding and debugging the problems you have with networks. TCP itself is based on four main algorithms. The first part is establishing network connections through a three-way handshake. Then we have acknowledgements on packet receipt, which is basically if you receive the message, then you send an acknowledgement. And then you have timeouts on packet loss. And then there's a closing sequence to end communication to like signal to the server that send whatever I have wanted to send, and does the same to the client. Now, the three-way handshake establishes the connection, and it goes something like this. Let's say you want to talk to your friend. You ask your friend if they want to talk. And if they want to talk, then you can propose that you keep track of your messages with numbers and set acknowledgements when messages are received. Luckily, your friend does want to talk to you, and then this message was numbered 42. And then your friend responds, and then they acknowledge the message numbered 42, and they send the sequence number 69. And then you acknowledge this message, and this is the three-way handshake. So both of you know that both of you are on the same page and would like to talk. Now, what happens when packets are lost? Well, the first case is you just send messages and then you can receive acknowledgements, and you can send more messages and you can receive acknowledgements. And what happens if a message is sent but then it's lost in transmission? Well, we can just wait for a minute, and because we did not receive a response, we can assume that either the message was lost or the response was lost. In either case, because we want to be sure that your friend has received the message, we'll just resend the message. Turns out we don't lose a lot of packets. This is just a good way to ensure that in case we lose 100 packets, this just works. However, this is slow because each of the message and response and message and acknowledgement takes one round trip time at least. So you can send multiple packets and your friend can send multiple acknowledgements. In this case, if some of the packets fail or some of them are not sent or sent out of order, then on sending the next packet, your friend can just respond that, oh, I do not have packet 48 because this was lost. And you can just resend the message which was lost. And then you can just send acknowledgement that I have received all messages until 49. This allows us to utilize the full bandwidth and send a lot more packets. And there's the closing sequence where you don't have anything else to send and you have sent everything you wanted to send. You just tell the server that you are finished with your communication and the last message received was this. And the server can acknowledge your message and say that this message itself was received. In this case, if any of these packets were lost, you can see that sending the packets again after like a minute timeout would just solve the problem. Next, we come to the hypertext transfer protocol, which is a layer on top of the transmission control protocol and is used for the sending files and data and API calls and so on. As with TCP, the client initiates a connection to the server and asks for a resource like a web page or an API, and the server responds with the resource. So we have three versions of HTTP. HTTP 1 has one TCP connection for each request, and it's kind of wasteful. And then the update to this is HTTP 1.1, which can reuse the TCP connection because the three-way handshake takes 1.5 round trip times, which is kind of wasteful. And then we've got HTTP 2, the next version.
Pausing for questions or comments.
Yeah, it is going well. I just wanted to mention that as a minor type of side feedback that I kind of lost for a minute when you mentioned that the pages were like larger than Doom. I didn't know what it was, and I looked like Page of Doom, what that means. And that turns out it's a video game, right? Yeah. It's just like a common reference that was lost.
Yeah, the video game Doom.
Yeah, but so far, technical part is very good. Thanks.
Okay, awesome. Thank you. So HTTP 2, we had a header compression, which allows it to take up less bandwidth, and then multiple requests can be multiplexed, and servers can push resources. We'll look at this in more detail later when we'll look at requests and like the timing graphs and so on. And finally, HTTP 3 is designed for speed and accuracy and has 0 round trip time and 1 round trip time handshakes. It actually does not use the transmission control protocol. So instead of doing like 1.5 round trip handshakes, it can do like 0 and 1 round trip handshakes with security baked in. So HTTP 2, well, this is HTTP 1, and you like send a request, you wait for the response, and then send another one, you wait for it and send it, and so on. In HTTP 1.1, you can send multiple requests as seen here, and then the server can send response in the same order, but at whatever time. This allows you to receive multiple responses. And then HTTP 2 allows the server to push resources as well as change the order in which the responses are sent back. So this is like the main page loading. And let's say the red arrow is an image request and the pink arrow is a CSS request. And then the server can decide to send the CSS back first before the image request first. And then HTTP 2 can also push the CSS and the image because the server knows that you're going to need the CSS file and the image for your HTML or whatever. The client can cancel requests if the client feels that they no longer need the resource, and the server can prioritize responses. Then we've got this HTTP 3. One of the problems with the transmission control protocol is head of line blocking, where messages are always received in the order they were sent in. If one of the messages was not received, then we have to tell the server that I have not received the message and then wait for the response. Only after that can we look at the messages after the message which was dropped, which means that even though we had the message which was not dropped with us, we won't be able to use it because of the guarantees that TCP provides. In HTTP 3, the streams are completely independent and it works on user datagram protocol in user space. So this is how HTTP 2 handshakes look, where there's a TCP handshake, and then there's the security part, and there's a TLS handshake, and then finally, after like 3.5 round trips, we can start sending data. However, in HTTP 3, we can just do that in one round trip. Then we've got CDNs. Whoa, what are CDNs? To get all of this pretty much for no cost, and by cost I mean like effort on your part, we can use CDNs. So content delivery networks are a globally distributed network of servers that mirror a particular resource. So if you have your web page, and they'll basically download your web page and send exact copy of your web page to your clients for you. So it's basically a bunch of servers that sit between your server and the client. This means that you can move the problem of managing latency, bandwidth, security, and so on, whatever the problems are about the link between you and your client, to a trusted intermediary. And the trusted intermediary job is to make these things look better. So they are really great at it. And they are usually distributed globally and share the server among multiple clients. The distributed globally part ensures that the latency goes down as well. They also increase security because they have better infrastructure and they have a lot more experience and better configurations and so on, makes things more secure. This is what it looks like. If you had a server in the US, this is the origin server. This is like the thing you're serving sites off. Before using CDNs, someone in South America would have had to send a request all the way here, get a response all the way here. Now, this server, the blue server, mirrors the yellow server, the origin server, and the requests are much closer geographically, and therefore the request responses are faster by a lot. As you can see, multiple clients can connect to the CDN thing and so on. Even if the CDN server cannot access the origin server at the moment, if the origin server goes down, the link goes down, the client will still be able to access your page because it has a copy in the desktop server. And finally, we're going to look at Firefox's networking tab to debug our network errors and why parts of a page might not be loading. It'll also show us why things are slow and why do they not work. So yeah, let's jump right into it. So Control-Shift-E on Firefox brings the networking tab. It looks kind of daunting at first, but it's basically divided into two parts. The right side is the timings graph, and the left side is just requests and then the responses. It tells you why your requests are failing. For example, this request is failing because of a CORS error, and then we can go ahead and solve the CORS error. Anyways, I'd like to focus on timings because this will help us get a better idea about HTTP 3 a lot better. Timings. It's like the first request, and then this is the request. It took 17 milliseconds for the DNS to be resolved, and then 52 milliseconds for connection, and then TLS setup, and then sending and waiting for the response, and then receive the response. As you can see, connecting, which is like the TCP three-way handshake, and the TLS handshake take ages. And we really, really like to not have this happen. Most of the time can be spent just here. In HTTP 1, waiting, handshake, and setup, and then receiving stuff. And then this thing is processed here, and then the browser requests a bunch more things, and then they are processed, and then it requests for a bunch more things and so on. And then if we look at the requests part, we can see that we made like 23 requests and transferred 192 kilobytes in so long. There were a bunch of 200 GET requests with response code 200, which means everything went all right. There are a bunch of 404s. So I can see that my logo was not loaded because the server did not know where it was. And my fonts were not loaded, which is like something that is really subtle, and I could never figure it out without looking at this. And then this is how HTTP 1 time graphs looks like. There's DNS resolution, there's connection, there's waiting for the server to respond, and then server response. And then once this is done, you can have a bunch more of these. The pink is the thing which we really, really do not want to happen, because the pink part means that the client is just waiting for the server to respond. As we can see, the next request cannot go through until this one has been processed. So this is bad. We don't want this to happen, which is why we've got HTTP 2. Here we can see that requests are sent pretty much at the same time. So there is no waiting time. This is really good. At the very least, you should upgrade to a HTTP 2 server. And then you can also see how the server pushed resources out of order. The first thing that was requested was this, the first line. And then after a while, a client requested this. However, the server had already pushed these resources before this was received or even requested for, because the server knew that this client was going to need these things. So server can push things, amazing. And then HTTP 3. As you can see, the graph here is a lot more sparse because they have been optimized as much as possible. So the first part looks fairly similar, but DNS resolution, the handshake time is reduced by a lot. and then we ask the server, and we wait for it, and then the server responds. The server can also start pushing things. You can finish receiving things in any of them, as opposed to the HTTP one, where you have to wait for this thing to be received before you can process the next one and so on. You can receive things out of order, and server can push things and so on. If you want to use HTTP3 frontends, I suggest Cloudflare is a great service. There's also others, but using Cloudflare is a no-brainer right now, at least for my websites. Yeah, and that's my talk.
Nice job, Pranav. This was super handy.
Thanks for having me.
Have a good day, everybody.
Thanks.
Thank you. You too.
Bye.